Ever wonder how AI can see a molecule or decode the intricate web of a social network? The answer lies in a revolutionary neural network architecture called pLSTM, short for parallelized LSTM, that's redefining how AI processes complex nonlinear data. Today, we're diving into the technical heart of pLSTM, its groundbreaking design, and how it's paving the way for smarter, faster AI systems. Let's break it down. Let's start with the basics. Traditional AI models like early RNNs struggled with sequences. Imagine trying to follow a recipe while forgetting the first step by the time you reach the end. Long short-term memory networks, LSTMs, solved this by introducing gates, mechanisms that regulate information flow, acting like a brain's memory system. But even LSTMs had limits. They processed data sequentially, which made them slow for long sequences and unable to capture complex relationships in structures like molecules or traffic networks. Enter pLSTM. This architecture doesn't just process data in a straight line. It navigates directed acyclic graphs, DAGs, which are like flexible, multi-dimensional maps of relationships. Think of a protein's 3D structure, atoms connected in a web, not a linear chain. pLSTM's design allows it to traverse these graphs in parallel, using two specialized modes to handle different tasks. Here's where it gets technical. pLSTM's P mode acts like a directional flashlight, propagating information along specific paths, ideal for tasks requiring local context, like tracking an arrow's trajectory. Meanwhile, D mode functions as a global ripple, spreading information across the entire graph to capture long-range dependencies. This dual-mode system solves a critical AI problem, the vanishing gradient issue, where traditional models lose track of long-range patterns. By maintaining information integrity across scales, pLSTM outperforms RNNs and LSTMs in tasks like molecular graph analysis and 3D data processing. To test pLSTM's power, researchers designed a challenging task, arrow-pointing extrapolation. Imagine an AI determining whether an arrow in an image points toward a circle. Traditional models, like transformers, rely on fixed positional embeddings that struggle with scale. pLSTM, however, adapts dynamically, maintaining accuracy even as input complexity grows. In experiments, it outperformed transformers on image tasks and molecular graph analysis, proving its scalability and efficiency. But pLSTM isn't the end of the story. In the 2020s, researchers made another leap, reimagining transformers as state-space models. Papers like Transformers, or SSMs, revealed that transformers and RNNs share a core principle: tracking information over time. The difference? Transformers use attention mechanisms to focus on critical details, like a team of experts each analyzing different parts of a puzzle. This breakthrough enabled models like Mamba, which processes sequences in linear time using selective state spaces, and Vision-RWKV, which adapts RNN-like efficiency to image tasks. Why does this matter? Consider a medical AI analyzing a 10,000-word scan report, or a climate model predicting trends over decades. Older models would slow down or lose precision. Newer approaches like Mamba's structured state-space duality let AI remember efficiently without computational overload. It's akin to teaching a student to take selective notes, focusing on key insights rather than every word. These advancements aren't just theoretical. Papers like Delta Product are refining how models update information, while open-source projects like pLSTM and Mamba are accelerating research. The result? AI systems that handle complex data, like protein folding or social network dynamics, with unprecedented accuracy and speed. So what's next? pLSTM and its successors aren't just models, they're blueprints for a new era of AI. By breaking free from linear constraints, they enable systems to tackle real-world problems with richer, more nuanced data. Whether it's decoding DNA, optimizing traffic grids, or revolutionizing medical diagnostics, the future of AI is being built on these foundational innovations. Thanks for watching. If you want to dive deeper into pLSTM, Mamba, or the math behind attention mechanisms, check the links in the description. Stay curious, and we'll see you in the next video.